Okay. Okay. All right. So we're gonna start today's lecture. So first of all, the scope of the midterm, I forgot to include in the email, I guess, but I'm planning to cover chapter 5 to chapter 8. So that's the normal model, Gibbs sampler, multivariate normal, and then the hierarchical modeling. So I'll of course send an email about this, but I would like to announce in class as well. So chapter 5 to chapter 8. And derivation wise, say back in the normal model, we did the derivation, so that's still expected. Gibbs sampler with the normal, we did that as well. Multivariate normal, we didn't do it, so that's not expected. And the hierarchical modeling, I did, I guess we did the normal case, but we heavily use DAGs later. So, but you still should know how to do it. I wouldn't, so try to go back to see, like, say the midterm 1. It's not gonna be, usually like the derivation wouldn't be exactly what we covered in class. It might be a new context, but you should know how to set up the joint posterior and then how to derive whether it's the posterior or full conditional. Yeah.
So I think I was such a very good homework. It's like several hours derivations. I assume you want anything that complicated on the test.
No, so I don't have the midterm 1 with me, but I think that would be a good place for you to review anyway, because back then those derivations are definitely new context, like different new models and then different parameters. But that kind of level is what you should practice. Yeah. And the solutions, yeah, no problem. And I posted the solutions to the midterm on Moodle as well. So, I mean, for the first one, so at least that will be something you can study with. But I just want to get it clear that because for the second half, we've been doing like combinations of JAX and then derivation and then try to code it up yourself. But I just want to get it clear that the normal, say like the semi-conjugate and then the conjugate. And then once we get to Gibbs sampler, we were still working under the normal model. So back then we did derive all of those, though in the end we started using JAX for doing analysis. So, but that kind of like the level of the derivation will still be similar. And I would say what kind of questions like that type of or that level of difficulty in the first midterm is a good indicator of what could be in the second midterm. Okay, say like some kind of derivation, say like the mixture that we did at some point in class, and as well as in homework, that would be too much for me to ask on the exam for the derivation. So I wouldn't do that, of course, yeah. But if it's some kind of, say, hierarchical modeling, brand new context, like different levels of the parameters, et cetera, yeah. So I would say midterm 1 should be a good place to go to, and solutions are posted, and yeah, okay, cool. So that's, there's that. And also just wondering how many of you will have to miss next Wednesday due to Thanksgiving? Oh, ooh. Okay, I guess I should have asked earlier. So pretty much everyone, I'm still happy to meet if we, yeah. Okay, let's see. Okay, so I guess we will cancel the class, but okay, so the thing is, it just be, I mean, because coming towards the end of the semester and then there's stuff due here and there, I just want to make sure that like the work that I would give will be well paced. Yeah, go ahead.
Did we maybe hold like a class specifically for projects?
Yeah, so that was what I was hoping for that Wednesday, but then if a lot of people are gonna be gone, but I can still, okay. Yeah, okay, so things I've been thinking is, so let me just tell you what I think we will get through by the end of the semester, and then we can see what we can do. So, first of all, the final project will be a 1 class time poster session. Okay, so that's gonna happen on the last day, which is that Monday, because Wednesday is Friday's schedule, we won't meet. So that Monday, December the 4th, will be the last time we meet. So, and then that gives us today, Monday, which is going to be a review. So the actual lecture that we will be able to have will only be the 2 times that we come back from Thanksgiving. Okay, so that Monday and that Wednesday will be the only time that we'll just meet as a class to talk about new material, case study, et cetera, et cetera. So there's that. And project, I think, so because there are only 2 lectures, 3 including today, are available, so I don't think I'll be able to make one like lecture to be able for you to work, but I can make more office hours available right after Thanksgiving. Yeah, to help with project. I don't think I'll be able to make one class for that. Otherwise, we won't get through some stuff. So okay, so the take-home part of the midterm will be due on that Monday. That's gonna be when we come back. So you have the, so on Monday, sorry, next Monday, you will get the, you will take the midterm, and then after that you would take the take home with you, the piece of paper, and then it's due a week later. Okay, so it's gonna be due on that class. So my plan is to return everything on that Wednesday. So that will be the last day of actual class that we're gonna meet. Okay, return the graded midterm, yeah. But again, I would like to allow corrections. So there will be some appointments available before, like from that until like the study period. Okay, so just watch out for emails and et cetera, et cetera. And then I do have one more case study that I want us to do. So I think I will just do it on that Wednesday, okay, the last class. Okay? So I will post it. We'll still keep the same group as before, but this time, whoever's gonna write, well, like whoever gonna come up with the write-up will be a different person from the group. Okay, but that, I mean, the discussion will happen the Wednesday after Thanksgiving. Okay, so today I'll try to go through as much as we can about the regression, but I do have some other topics that I want to cover if possible. So I will try, like, I will see how much we can do by today, and then we can plan for that. I mean, the thing is, I think by now people are pretty tired and trying to get ready for exams and stuff, so I try not to put in too much new stuff. And I understand that each of you might be doing challenging project, so you might have more specific questions that I want to ask instead of like learning something new. So yeah, trying to strike the balance, but this is pretty much what we'll be do before the end of the semester. Okay, all right, okay, so for today, I guess let's start going back to the multivariate normal a little bit, because that was, I guess, was a little bit too fast, I think. And give me a second. So that was, okay, right. Specifically, I want to go over the example. But back then, the multivariate normal, we were doing it for p dimension. So the case where you will use any kind of modeling technique like this will be you're having a p dimension response. I say like p dimension observation, I should say, for each observation. And then you will model, you want to model it as a multivariate normal, and the example that we had was the pre and post instruction score of one person. So that was the case that might be like suitable to do multivariate normal. And in fact, I was actually trying to figure out if there are any more interesting examples out there. And I realized a lot of people don't do much multivariate normal modeling in some sense. So first of all, data usually does not arise in that way. And then a lot of times people are going to end up doing a regression instead of like model things jointly. So I think that will be why we haven't seen much of it. But I do want to point out that, say, in 7.3, that's in the exercises, I just read through a little bit. Like they have an exercise of Australian crab data. So they have two kind of crabs from Australia, and then they have the measurements of their body depth and their real width. Okay, so actually that was an example. Say you might be able to model this too as a bivariate normal. Okay, so again, this is not pre-post kind of data, but it's still one observation. You have multiple, I wouldn't say responses, multiple observations for one item. Yeah. And there are other types in 7.4, for example, they're looking at marriage data, and then they're having multiple variables, and they assume that you can assume that they jointly distribute in the multivariate normal sense. So again, I don't know much else in terms of what are the popular examples that people would use multivariate normal. But I do want to tell you that now we're doing regression, the multivariate normal actually becomes very relevant. You will see that like the derivations later for the regression cases, multivariate normal becomes very commonly used. Okay, so it's still definitely useful, but then in terms of using it itself as a modeling technique, not that widely used. Okay, but right now we're dealing with this pre and post score, so it's a bivariate normal. So I want you to, right, so the data set was 22 pair of scores of students, 22 different students, and it's pre and post. So I want to go over a little bit as how they actually set up the prior for this case, because you might, some of you were reading through and then trying to figure out how they come up, say, the priors in this way. So first of all, so for the multivariate normal, you have two parameters, right? One is the mu, which is the p-dimension mean. The other one is the covariance matrix. Okay, so for the mu, which is the mean, this will be the type of prior that we do for a semi-conjugate case. And then you're going to do a Gibbs sampler. So the way to come up with a mu0 over here, which is what mu centered at. So mu, so first of all, let's see. This is the sampling model. Okay, sampling model is this way. Okay. So for each person, you have two scores, and we assume that it's a bivariate normal center as some mean, and with the covariance matrix sigma over here. So now we have two different priors that we have to specify. First is for this mu, and the other one is for the sigma. Okay. For the mu, we know that the semi-conjugate case will be a multivariate normal, like bivariate normal again. And for sigma, it's going to be an inverse reshared. Okay, so we're going to do it one by one here. So for mu, the way that you can do is say, because both tests designed to have a mean of 50, so it makes sense if you're going to put a bivariate normal there, the mean is centered at 50. So that's why they're doing this 50, 50, and then transpose. So the correct dimension is a 2x1 vector for mu0. So that's the mean that the mean should center at. That's how they come up with it. And also how to set up this lambda 0, which is the prior covariance for the mean. So if you believe that the true means not likely to be less than 25 or more than 75. So because it's from 0 to 100. Okay. And you let it center at 50. And then you think it's most likely between 25 and 75. So this is the range that this prior is trying to capture. So the way that we do it, because this lambda 0 is going to be a 2 by 2 matrix, right? So you have to specify the off diagonal to be, the diagonal to be the variance, and the off diagonal to be the covariance, right? So the variance, in order to reflect that each of the scores should be within roughly this range, you'll pretty much work it backwards, that 50 is the mean, plus or minus 2 times the standard deviation. I would like it to be in this range, and that 2 is similar to like 1.96, like assuming it's going to follow a normal. Then you work backwards, you realize that you can put the variance to be 156, and that's how you get that. Okay, so you center at 50. I want this go back, like not go below 25 and not go beyond 75. So I want to control the variance in this range. So then I work backwards to get my lambda 0 square. And it's 156 for both. So you see that on the diagonal, it's 156. Okay. While here, the off diagonal is trying to get the covariance, right? The covariance will be the correlation multiplied. The covariance, this covariance will be the correlation multiplied the square root of the product of the variance. Yeah, so that's the definition. So if you think it's just 50, like correlation is mediocrely strong, then you put 0.5, and that's how you're going to get 156 times 0.5 to be the off diagonal. Okay? So that's how you set it up. Okay? But of course, if you have, I don't think it's only going to be between 25 and 75. I want to say it's between 10 and 90. Then you're going to work backwards again to figure out what is your lambda 0. Okay, and that's going to transfer, like change this value, and that change the diagonal. And then of course, sometimes, I don't think these two scores should be that related. I only want to put 0.1, then that will be how you come up with the off diagonal. Okay, so that's the general idea. But again, depends how you believe before you start. So that's the prior for mu. And the other part of the prior is going to be for sigma. Okay, so again, the data model, let me write again over here. The data model is this. So we're trying to put a prior for sigma square, okay? For sigma. So sigma is 2 by 2, right? And this again is trying to tell you, so 2 by 2, diagonal will be the variance, and off diagonal will be the covariance, okay? So the diagonal, again, so the way, one example how you can do it is because the scores are constrained to 0 to 100. So if you think about how variable that sigma is, especially on the off diagonal over there, will be, say, it's centered at 50, but it's not, like it's bounded below by 0, bounded above by 100. So again, if I assume it's approximately normally distributed, I will figure out what my sigma 0 square is, which in this case is 625. Okay, and again, I put a correlation over there, about 50%. So you see here's 625, and the off diagonal is half of it. Okay, and one last thing is about this Wishart inverse Wishart distribution. We didn't get into detail too much about understanding that particular distribution, especially the parameters. But a rule of thumb, if you want to put very vague belief about your prior, the rule of thumb is you're going to plus 2 on top of the number of, like the dimension as your first parameter. Right? So following that advice, if I don't have strong belief about it, it's a bivariate normal, so P is 2, so I put 4 over here. And that's all like what you did over there. Okay. So yeah, so if you work through the precision matrix, it's going to be Wishart. If you work through the covariance matrix, it's going to be inverse Wishart. Okay, so those are, I guess, the parts that we didn't get to talk about, and this was the full conditional and stuff. And then in the end, asking the questions how to do it. So I do want to show you really quick on the of the code really quick. I didn't assign, I mean, I will give one final homework, but only 2 questions. One from multivariate normal, the other one about regression. I didn't want to assign it now because I think you have so many other stuff to do, but so that's why I'm trying to give it later, but now I still want to talk about the code a little bit, is how you can do a multivariate normal analysis over here. Okay, so I showed it pretty quickly last time, but let me just go through it a little bit. So you will need to, because now as you imagine that we have to, like the full conditional is a Wishart, and then, or inverse Wishart, and then a multivariate normal, right? So now we need a new package called MVT norm, multivariate normal, for you to sample from that. Okay, so that's the first package over there. The other one later also useful, and then CODA as well. That's what we do. So you will, let me see, give me a second, let me set it. Okay, wait, so let me bring in the data. So the plot over here right now is showing you the post against the pre, and we're saying that this is telling us there is some, of course, some relationship between these two, and using a multivariate normal, in particular bivariate, might be a good choice. So the way that you're going to do it, so let me bring up the code right here. Yeah, so first of all, I'm coming up like this is just set it up. I have the Y bar, et cetera, and then this is where I set up the priors. Okay, so this is the part that we just went through. Okay, so for this is the mu 0, right? 50-50 that we did, and then this is the lambda 0. That was the 2x2 matrix that I did, and then the inverse is using a SAW function. Okay, and then mu 0, that's the first parameter for the inverse Wishart. That was 4, as I said, I was trying to set up a really vague prior. And the last one is the sigma 0. That's the prior for in the inverse Wishart distribution for the variance. Okay? And I also set up iterations over here. And then in this case, you notice that because now my mu is 2x1, right? So when I save my draws, I need to save it in a matrix. Okay? It's not just one scalar anymore. And phi is 2x2, so we're saving a matrix in that way as well. And then similarly for sigma. Okay, so this will be the big difference from before. That in the past, we're only saving, because the model is not multi-dimension, we only have scalar, not only for the observation, but as well as for the priors, et cetera, et cetera. So you see that for the parameters, I should say. So you don't do matrix, you just do like REP and then save over there, but now you need to initialize matrix. So here I'm also just initializing the values using from the prior. So this is the first time that I'm using the random draw of a multivariate normal. Okay, so it's RMB norm. And then pretty straightforward, you tell R how many you want. We want 1 for now. And you're doing the mean to be mu 0 and the variance to be lambda 0. So you just draw from that. Okay. And here I'm just start to save the first one, and then phi is the inverse Wishart. Oh, sorry, phi is the Wishart, so you do R wish. Okay. And then the prior, the first parameter and the second parameter over here. Okay. Yeah. All right. So the Gibbs sampler, you see that pretty much only 2 parts, because I only need to update mu. which is going to be a multivariate normal, and then update phi, which is going to be a Vassar. Okay, but the parameters will be, I mean, each of the terms will be more involved. You just refer to the full conditionals I showed you before. So this is, so again, change from before will be this part you're doing matrix multiplication. So you need to have those signs. And we saw solve before, that's doing the inverse. And then here is, again, random normal draw, random multivariate normal draw. And here is the inverse Vassar. Yeah, Vassar, yeah. Yeah, so sweep is working like apply. Yeah, so this is, so if you remember, which I doubt, in the full conditional, there will be terms that you have to subtract the mean from the y and then take the square, et cetera, et cetera. So that's actually trying to apply on the, like on the vector. So you subtract the mean from each of the y, and then you do it, you multiply it with another thing. So I'm using sweep as like a shortcut to do that. But it's pretty much doing, I mean, it is doing exactly what is shown in the full conditional. Yeah. So you know apply, right? Like you have apply function will be you do apply. So I can show you over here. Say if I have a matrix, I want to apply the same function across all of the rows, then I can do apply. And then the name of the matrix, if I want to do row, I think I will put 1 as the second input, and the last one will be the function that I need. Okay, so this is similar over there, but sweep is in particular like get it off from that. All right, and then the last part is saving the record, and then in the end is to convert it to MCMC objects. That's using the CODA package, and then trace plot, et cetera, down there. Okay, so yeah, I didn't get the chance to prepare Jack's code for this type, but again, I would say if you're going to do a multivariate normal, pretty much things are derived and they're all in that form. There won't be any kind of variation anyway, because it's not that you're putting it, unless you put different priors, of course. If you don't want to use the conjugate over there, you can do it, but usually people are actually going to opt for the conjugate, and you're probably going to end up doing, and you see that it's not that hard. It's just like 5 lines over here, and then you are pretty much done with your Jacks. Sorry, with your Gibbs, and I think that's actually a good place to learn. Okay, so this is the code, and yeah. So I was assigning just one homework question: the analysis application of a multivariate normal. Probably just the Australian crab example over there, so you can just get a handle of it. Okay. All right, and that's all I want to talk about the multivariate normal, but again, it's not that widely used out there. And I think a lot of times it's because the data does not arise in that way. And a lot of times I mean, think about it. You put a really strong assumption about this model. You assume that all of the variables jointly follow a normal multivariate normal distribution, but a lot of times they wouldn't. That's why people don't use this, because this is not that very flexible. Okay. All right, and okay, so there's that. Yeah. Okay. Okay, so the other part that we can keep talking about is the regression. So regression actually has a lot of interesting stuff. But today I want to go over, so give me a second. Last time we got to the point to talk about the model setup, I think. Yeah, so regression is really trying to understand the response as a function of the predictors, okay? And in particular, the underlying model over here is a normal, okay? Normal in the sense that because you assume, I mean, that's for frequentist as well, and that's why you see all of those parameter estimations. So say this is a 2 predictor case, no intersect, and the expectation of y given x is fully specified in a linear combination here. It's something about x1, the first predictor, and something about the second predictor. Okay, So if you specify a model like this, the mean is in this relation. And this is the only part that is bringing the variability. Okay? So because you put, say, a standard, a usual, pretty commonly used linear regression is doing an IID normal center as 0 and some variance. So this is the only place that introduces variability into the model, because this is fixed. And this is the part that you put the variability. So in this whole model, there are multiple parameters here. People are curious about beta 1, because that's the coefficient on the first parameter. They're curious about beta 2, the second parameter, because we're only doing 2 predictors here. But they're also curious about sigma square, okay? Because that's the part that you assume the random error like the variance of the random error in the normal distribution. So usually people are gonna make inference about all of this, okay? Yeah, so that's how the model is set up, and this is true for both frequentist and Bayesian. So I just want to show you how you can actually put it into a multivariate normal representation, because that's what you're gonna see mostly if you're doing Bayesian type of linear regression. That's how things are done. So pretty much we know that at the individual level, this is the model, right? You have all of the errors. IID follows a normal distribution 0 sigma squared. And then each of the observations. So here, this is I'm just trying to work out the dimension. Okay, so it's beta. Beta, this is a vector. Beta transpose. And then this is the vector as well. Depends on how many predictors you have. And this is a scalar. Okay, so this is just trying to make sure that it's going to be a 1 by 1. So that's how you're putting the dimension, right? Okay, so if you try to write the joint likelihood, you actually know what it is. So if they're all IID, then each of them is a univariate normal. So you can have the normal kernel over here. So I already brought the product over here. So that's the effect of n. Okay. And down here, you see that this is the sum of all of the difference. Okay, so okay, let me maybe write that first. So if yi follows normal beta transpose xi and sigma squared, then yi given say beta xi and sigma squared, the density is a normal, so you have 2 pi squared, 2 pi sigma squared, square root of that, and then in the exponent you have negative 2 sigma squared yi minus beta transpose xi, and then take the square over there. Okay. Yeah, so this is taking the product and simplify, and then you get to this step. Okay. Yeah, so the effect of the product, because they're n product over there, so the effect is raised to the power of negative n over 2. And then over here, the effect of the product outside the exponent is going to be a sum inside the exponent. Okay, so this is will be what you would do if you don't know about multivariate normal. But if you think about it, you can actually write it in terms of multivariate normal, but not in the same way as what we have seen before. It's actually a simplified way. Okay? So let me just describe this a little bit more. So this will be the entire data set. Okay, this will be the entire data set, and because your response is univariate, so this will just be say all of the y1 to yn, then transpose over here. So if you think about the dimension, just be n by 1. Okay, and each of this will be y1, y2, yn over here. Okay, and then it's going to be a multivariate normal with dimension n, because that's what I'm doing right now. And then in the mean, In the mean here, you will have the mean vector, and then covariance covariance matrix. Okay, so just based on definition, you know that the mean vector will be n by 1, right? And the covariance matrix is going to be n by n. Okay, yeah. So this mean, each of the mean is just going to be exactly what we have seen before. Okay, because each yi at the mean is beta transpose times xi. Okay, so say over here, you have beta transpose x1, beta transpose x2, until beta transpose xn. Okay, and you notice that here we write x times beta. That's just how the dimension will work if you bring it into a matrix. Okay, but on each of this, it's going to be beta transpose xi, and that's a scalar. Yeah.
Do I want to have the transpose for the n, because if x is an n by p matrix, then p by 1.
No, x is actually p by, oh, let's see. X is n by p.
Multiply by beta. You can n by 1.
Oh, yeah, let's see. There might be a mistake when I wrote it up. Let's see. So x, if x is an n by p, and then beta, oh, sorry, so beta, yeah, I think I probably made a mistake over there about the dimension of beta. I think like the beta vector over here, I will go back to fix it. And I have to think through, I mean, those like dimensions pretty complicated over here, but what I'm trying to do is this is x is n by p, and then I think multiplied with beta, which should be a p by 1. Yeah, 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 sorry about that. I will fix, okay, so Eli's question is here, like just the dimension here. I will fix this, but once you do it, you have your x times beta, this should be an n by 1. Okay. I think so, yeah. Yeah, over here, yeah. Thank you. Yeah, so it should be a transpose over here. Okay. Yeah, okay. Thank you. All right, and then if you look at the covariance matrix here, because what we're doing, we assume that each of the observation, like each of the error is actually like normal over here, right? I mean, they are not dependent at all. So if you're assuming, if you try to write it into a multivariate normal, you're actually only gonna have the diagonal, you're gonna have sigma square, sigma square, sigma square, but all of the off diagonal are gonna be 0. Because you assume all of the observations are independent. Right? So at each level, I mean, at each observation level, you have them to be IID normal. So if you want to write it into a multivariate normal, you're only gonna have the diagonal to have sigma square, while the off diagonal are gonna be 0. Because the covariance matrix, this n by n covariance matrix, is telling you the covariance structure of all of the observations here. Okay? So in particular, for this multivariate normal representation, because they're all independent, so the off diagonal, which tells you all of the covariances, they should be 0, while the diagonal is talking about the variance, so it should be sigma squared. Okay? So this is what I mean by a simplified or like more specific type of multivariate normal here, because in the previous chapter, we're talking about multivariate normal, say like for the bivariate case, when you have 2 by 2, like pre and post scores, and over there, because there's some covariance going on, like correlation going on, so your off diagonal wouldn't be 0, okay? And that's I would say like a more true multivariate normal in some sense. Here, it's just because later all of the computation will be more simplified if you're doing a multivariate normal representation. So now we move to multivariate normal, but the covariance structure is in that way. Okay. All right. So okay. So this will be this particular multivariate normal representation. So you would imagine that now move forward, we're gonna, for all of the derivation of different priors and posteriors or full conditionals, we're gonna have the multivariate normal involved. But again, I'm not gonna require any of that for the derivation, but I do want to talk through several kinds of popular priors that people put, and then go through them just like pretty like quickly, in the sense that you know what is each type about, and the advantages and disadvantages of each, to see where you're gonna, like in the future, if you were to choose which one to use, you're gonna have some idea to rely on. So first of all, if we start writing things in terms of multivariate normal, this will be the likelihood. Okay, so likelihood over here, this is what we learned from last chapter. That's the entire PDF, the joined PDF. And I put in a proportional because I want to focus just later how I'm going to put prior if I want. Okay, so pretty much this will be the contribution, like this together with this will be the contribution about sigma, right? And all of this here will be the contribution about beta. Okay, so that's why I throw away this, because this is the data, and I throw away the 2 pi whatever over there, it doesn't matter. So this will be the joint likelihood. Okay, so I guess this will be a quick review as well of all of the model that we've been doing. So this will be the likelihood. And if you just look at the form, because now we need to put priors for beta as well as sigma. Okay, beta here is a vector. Okay, sigma here is a scalar. So based on this form, what would you guess if I want to have full conditionals recognizable later? I need to put something in here for beta, and then combine with the likelihood, I can find something else that I know, and sigma squared similarly. Right? So what would you do? What would you guess? By the way, all of this is in matrix form, but once you do all of this, it's going to be a scalar. But just so you know, sometimes I think all of the dimensions would put people off a little bit. But this will be a scalar. So beta might be a little bit more like difficult to think, but what about sigma square? Traditionally, for the univariate case, we put inverse gamma, right? And we recognize it's going to be inverse gamma because it's going to be raised to some power here, and then in the exponent, it's negative times something multiplied by that, right? So actually in this case, for the semi-conjugate prior, we will be able to use gamma or inverse gamma again for sigma square, okay? And for beta, I guess if back then I required all of us to derive for the multivariate normal case, you probably will have a better guess. So here, the semi-conjugate would be a multivariate normal as well. Okay. So back then, in previous chapter, when we're doing likelihood to be multivariate normal, mu and sigma squared, sigma, and then the semi-conjugate prior that we put for this is another normal. Right? Yeah. And I didn't require it, but back then, I hope you got the idea that if you put a prior like this for mu, you will get full conditional recognizable to a multivariate normal. Okay, so this here is actually very similar. For beta, you work in the same way. Yeah.
You know, multivariate normal, the first part was the determinant of covariance metrics. Sigma squared, the determinant of sigma squared I.
Sorry, so no, sorry, say it again, sigma squared.
Sigma squared sigma squared times that.
Yeah. Yeah, right. Yeah, because it's an identity matrix over there. Yeah. Okay, so here, the semi-conjugate prior that we're gonna do, again, for sigma squared, gonna be an inverse gamma. And then for beta, it's gonna be, here, the dimension is P. So it's gonna be a P by 1 multivariate normal. Okay. All right, so I'm just gonna show you over here. So the easiest one to put will be a semi-conjugate in this way. They're independent from each other. Beta is going to be a p dimension multivariate normal, and sigma squared going to be 1 over like inverse gamma. Okay, with parameters over here, very generic, as we have seen before, and not required, but you will be able to, if you want, you will be able to derive the full conditionals. And it's a little bit involved, but again, to me, like all of this look very similar from before, the multivariate normal case. But in general, I want you to see that, again, the posterior covariance, if you think in terms of precision, this is prior precision, data precision, right? And similarly, for the mean, once you have the covariance matrix or precision ready, this is the weighted average of the prior mean and the sample mean. Okay, so all of those are recurring themes, as you can see. And 1 over sigma squared are going to be a gamma. This is prior sample size, data size. And then this is the sum of squares from the prior. And this is sum of squares from the data. Okay, so here you notice that I highlight in red because we're going to go through some other priors as well. And some of them going to give you full conditionals ready. Some of them, so in that case, you will use a Gibbs sampler. But some of them actually, depends on how you put it, but some of them actually going to just give you posterior directly. So you don't even need to use Gibbs sampler. Like a regular multicolor approximation will be good enough. Okay. Okay. Right. So, all right. So another type people actually use is called Jeffreys prior. This is a limiting case that you let the prior variances go to infinity and the prior sample size for the variance goes to 0. So this simplifies to be the joint prior of beta and sigma squared, which is going to be proportional to 1 over sigma squared. Okay, so this is going to produce you a different set of full conditionals, but this will give you, yeah, once you have this, you will be able to use Gibbs sampler. And this type of prior is is non-informative. You're just using proportional to 1 over sigma squared to put a prior like that. But that does give you recognizable full conditionals. So this will be another set of things that you can do. Okay, all right. And yeah, I put some connection to the maximum likelihood estimate if you know about that from other courses. So it turns out that the posterior, like the full conditional of the beta, the expectation would just be the MLE, and the variance will be the variance of MLE. So that's another feature of why people want to do it. Because if you do Jeffreys prior, you will get to results very similar to a regular frequentist classical inference of linear regression. Okay? So that will be another attraction to people. This is the prior distribution I actually want to spend a little bit more time about. And it's unfortunate that we only get to this like to pretty much towards the end of the semester, but among the papers that I posted online that you said, that I said you'll be able to use as your project idea, actually there's a really nice paper about this Zellner's G prior. That's a really popular prior for linear regression, Bayesian linear regression for beta in particular. So beta, as you can see, eventually we're going to center it at 0. And the variance that we're putting, so first of all, I mean, the general structure is still the same, okay? Beta has a multivariate normal, and then 1 over sigma squared going to be a gamma. But in particular, we're putting the variance, covariance matrix for this beta to be G, which is something that we'll talk about, times sigma squared, and then times X transpose X to the power of inverse, or like inverse of that. So the derivation and as well as the results looks a little bit involved, I agree. But there are really good features about this type of prior. So pretty much this G is trying to control. And I would say, rule of thumb is actually to put G related to the data. So G is a positive constant, and you see that G will be able to control how much you're getting from the MLE and then from the data over here, okay? So let me actually go to this slide to talk about the results. Before that, notice, oops, sorry. Okay. Yeah, so the Zellner's G prior in this case, actually, because you get all of the posterior distributions directly, so you don't even need to do multicolor, you don't need to do MCMC like Gibbs. You can actually just use multicolor techniques. And people like to use it because people also like to compare and then borrow information from the frequentist methods. So the Bayesian estimate of the beta actually will shrink the usual MLE, the LS least square estimates in the frequentist method using the ratio of G over 1 plus G. Okay, so that's why earlier I was trying to show you the effect of that. Okay, so we're trying to, so pretty much in short, Zellner's G prior is trying to get useful stuff from the LRS estimate, which is from the usual frequentist analysis. And then it will help you to shrink it. So variability will be smaller. And usually G is equals to the number of observations to represent vague information about beta. And another really key attractive feature is the G prior is invariant to reparameterization. So sometimes you might want to reparameterize your model in a different way, or even just change to a different unit scale. And then this prior will still just work in the same way. Okay, but in short, in order to use it, this is the posteriors, so you don't even need to do Gibbs sampler. Okay, so that's another good feature about this. And this is the demo that I have in this in the code. And I think I'll skip this one. But the last one I want to talk about is you might wonder why I should put a joint multivariate normal for all of the beta, right? Why can I just put independent univariate normal for each of the beta? So each beta is a coefficient for each predictor. So far, we've been doing it jointly, right? But you might be wondering, oh, why I cannot do it as a univariate normal? So sometimes you might want to do it. So first of all, the unit of measurement of all of the predictors are the same. And also you actually have to center all of the observations. And also the predictors to have mean 0 and variance 1. So I think this is also a standard practice in the frequentist regression as well. So if you do that, you will end up having your normal priors in this way. Okay, so notice this is a univariate normal. This is normal 1. So I'm only focusing on each predictor, like one coefficient at a time. And it's going to be IID, center at 0, and with some parameters multiply with sigma squared. But of course, if you write it in terms of multivariate normal, it will be the same. It's going to be a mean vector 0, and then an identity covariance matrix. I mean, identity multiplied with the values over there. Okay? So the motivation over here is we should try to put independent prior on beta j, because we might be able to do it, especially under those conditions. And then you would do it in this way, but equivalently, you can express it in the multivariate normal. And if you do that, you will see that if you derive the results, so actually you don't need Gibbs sampler again, because this again will give you posteriors, and you will be able to use Monte Carlo directly to do all of this. Okay, so I agree there's a lot of stuff going on. There are multiple different ways to put priors for this case. So I try to provide like a summary table like this. But again, it's going to be problem specific in terms of which kind of prior that you want to use. So, but in short, if you do semi-conjugate and Jeffreys, you're only going to get the full conditional. So you're going to use your Gibbs sampler. And I wrote it down over here. For Gibbs sampler, you either code it yourself or use JAX, whichever should be fine. And for Zellner's G prior, the unit information I had the slides, but let's not worry too much about it. And the independent univariate prior that I talked about at the end, all of those you'll be able to use Monte Carlo to do it. Okay, so since Zellner's G prior is widely used, so the example that I have is a sample code for doing the Zellner's G. So let me show you the problem and then just walk you through it about the idea. So I'm following the textbook. So if you have it, it would be good to put it out as well. It's in chapter 9. So the data set is the oxygen uptake, okay, from a paper in 2000. So what they were doing is they have 12 healthy men who did not exercise regularly, were recruited to take part in a study of the effects of 2 different exercise regimen on oxygen uptake. So they put them into 2 different groups. 6 of the 12 men were randomly assigned to a 12-week flat terrain running program, and the remaining 6 were assigned to a 12-week step aerobics program. And they measured the maximum oxygen uptake of each subject. So that was the response variable over here. And that was the difference before and after the program. So the interest is how a subject's change in that uptake may depend on which programs they assign to. So in particular, in the same data set, it tells you the indicator of which program they're assigned to. So 0 if it is on the running program, 1 if it's the aerobic program. And they also tell you the age of the subject. And they're in particular also interested in the interaction of the program and age. Okay, so I hope you brought your laptop and the data set. I posted on Moodle as well, so you will be able to download the CSV. And I want to walk you through using the Zellner's G prior. So R code on Moodle, CSV on Moodle as well. So since you all have laptop, I will actually bring up the full the posterior distribution of the Zellner's G prior situation, so you can compare. Yeah, so the posteriors are in this form, and that's how I was sampling using multicolor. I want you to get a sense of, if you don't use JAX, how the Bayesian linear regression can be done. For this one, you don't even need to use Gibbs center. We're just using multicolor approximation. So if you download those, save to your desktop or save to your laptop, you'll be able to run it. And try to spend some time understanding the code. Maybe just just not like here, so just not yeah, I think you're good. You have to install it before you have to install it. Yeah, so this one, yeah, because I didn't put it there because I had it installed before. So the T1. Yeah, the multivariate normal you have to. Yeah. So that one is used to draw the phase. Okay. Sorry, I think there was one problem with the code that I forgot. So you might, yeah, sorry about that. So if you go to, I guess it's about line 25, 26, because I probably forgot to update upload the latest version. So over here, there should be beta over here, V beta. Sorry about that. So line 26, sorry, yeah. So if you change it to be V beta instead of VB, that should run. So I can try to run it here as well. Yeah, so the code, I think, should run pretty quickly. And then the last few lines are trying to get you posterior means of the 4 regression parameters, the variances or standard deviation of them. And then lastly, to get some plot of the coefficients, because that's the thing that you want to make inference about. Okay, so make sure you get through the code, and I would like to point out certain lines that I think are useful. And then towards the end, you should be able to plot it to make inference. That's a solve, so that's maybe yeah, that's our function. And T is transpose.
What's line?
See line? Yeah, that's column line. like I have multiple columns and I try to combine them. Yeah. Yeah. Yeah, they're definitely like little things here and there that you might not see before. And with this data, you can as well just run a regular classical regression using the LM function in R. So this is using the Zellner's G prior, but we went through a couple of other ways to put prior and then to do the sampling. So I would like to just ask for this to be the last homework question that you run it on different type of priors to do it. So this code is specifically doing the Zellner's G, and you have 4 predictors. You have an intercept, and then the program indicator, the age of each observation, and the interaction of these two. Okay? So pretty much, so that means you have beta 1, beta 2, beta 3, beta 4. Okay? So the Zellner's G, because you have posterior distributions, you don't need to use skip sampler. So if you go to line 16 to line 22, those 2 lines are drawing S, which is 1,000, number of draws from the posterior distribution for sigma square. And then if you go to line 24 to line 37, those are the lines to draw the 4 different betas. Okay? And because the posterior distribution is a multivariate normal, 4 by 1, dimension 4. So that's what you're doing. So solve is getting the inverse. T is transpose. Okay. And the last, especially the last 2 plots over here, if you plot it. So for beta 2, which is the coefficient of the second predictor, which is the program, you see that, I mean, I plot it as a density over there, but you can always also do a quantile to see the 95%. So if you do that, yep. So this tells you that the coefficient, oh sorry, yeah, Katie. Oh yeah, the coefficient, if you do a quantile. So first of all, from the plot, you see that it's not that far from 0, right? This is a coefficient. So if you think about, this is telling you the effect of that predictor. So if you do a quantile, like I do over here, 0 is in this 95% credible interval. Okay? So this will be like a similar or analogy to what usually will make your inference in the classical regression as well. That in this case, 0 is in the 95% credible interval. So this is probably not a significant predictor. Yeah.
So are these 2 plots for 2 of the 4?
Yeah, it's only 2 of the 4. Yeah, I was doing. Mm-hmm. Good question. So think about, okay, so Katie's question is, because it's 4 different predictors, right? And in the Zellner's G prior, okay, so just give me a second, I need to bring that back. So Katie's asking a good question about how was the prior was set up. So yeah, so this Zellner's G prior in particular, especially if you look at the beta. So here in this context, is you have 4 predictors, right? And then the prior that we put for beta, it's a multivariate normal dimension 4. And in particular, we set 0. So that beta 0 is actually 0. So you're setting prior that I think marginally all of them are, oh, no, sorry. Marginally, they're not exactly the same because you have, say, like the data over here. Yeah, so this, exactly, yeah, right. So that's how, say, yeah, it's hard to do back and forth, but in the code, that was what I was doing for the first few lines, okay? Yeah, so, but again, all of the priors, so don't worry about the covariance here, but the mean, all of the betas, beta 1 to beta 4, they're all centered at 0. Okay, so at least that is true. And then this dimension over here, well, I mean, all of this axis data, right? So all of this, so each predictor gonna be related to its observations. Yeah, but it's related to its observations in this particular setup. Mm-hmm. Yeah.
We also use more data prior to 0 so that the posterior exam like evidence against 0.
Good question. So here, I guess you will, like the way that you put the prior, say in this way, will be that I believe all of the coefficients are not important to start with. Yeah, but I think you can start at different places. It would just be like the derivations probably won't be as good as what you can see over here. Yeah, but then again, if you do injects, I would imagine you don't have to worry too much about that. Yeah. Mm-hmm. But a standard practice is to center all of them at 0. Yeah. So yeah, so next question is about, I guess this one's, yeah. So you can, I mean, you set up a beta 0, but only if beta 0 is 0, you will get nice posterior in this way for the Zellner G prior. But the implication of putting those to be 0 is saying that a priori, you believe all of the coefficients are around 0. Okay. Yeah, so you see that, like, so for Zellner's G prior, this is what you can do. And if you get back and forth to see like the Jeffreys prior, you should be able to code it. It's not that hard. It's full conditional, so you need a Gibbs sampler, but you at least be able to run the analysis. The semi-conjugate is very similar as well. You have the full conditional, so you can do it. And the last one that I talked about is even more simpler. I guess it's the independent prior, because this case you have posteriors, so you don't need Gibbs sampler to do it. But they're all, I mean, it depends on the situation. One will be, I guess, preferred than the other ones. And the textbook actually was only doing the Zellner's G because I think it's the most popular one, where it really has this invariance quality, as well as you can control the shrinking to the of the ordinary least square estimates. So I think that's why people do it. But again, it doesn't, yeah, you should actually also try the other ones, which will be interesting. And so you notice that for regression, model still the same, you just estimate it in a different way. I mean, it's still like regression, each observation, the expectation will be a function of the predictors, and then you put a normal error over there. And everything in Bayesian linear regression works through multivariate normal. And depends on how you set up your prior, you might get posteriors where you can use multicalo. But if you only get full conditionals, you get Gibbs sampler. And then towards the end, how you're going to decide whether those parameters or like those predictors are significant or not. You're looking at the either 95% credible interval, like quantile based, or the HPD, if you still remember the highest density, the highest posterior density, highest posterior density credible interval. But the rule of thumb is, I think, usually is if 0 in the interval, you will probably drop that predictor, things like that. Okay. Yeah, so yeah, time is up. So I hope you get at least a general idea of the approach. And it is a lot of information, but I hope a good number of you have seen regression before, so this might not be too fast. But there are definitely like certain technical stuff that you have to go through. But in the slides, I list all of them, say like the full conditionals and posteriors. So those will be the places that you can start doing your analysis, like start coding up. And so yeah, so for the last 2 lectures, like the week after we come back from Thanksgiving, I would do say like 1 case study and then bring in some other examples in terms of regression that you can see some other applications. In fact, if some of you were doing regression for other classes, if you have an interesting data set, feel free to send it to me. I'm happy to use those to demonstrate instead of me finding something that might not be that interesting to you all. Okay, all right.